When we test power series for convergence, there's two things to consider. First of all, what are the values of x that it converges? So this is a radius of convergence, and for this we use a ratio test. And then secondly, we need to test the endpoints to figure out the interval of convergence. Do we include the endpoints of that for that interval, or do we exclude the endpoints for that interval? So we start with the ratio test, and then we test the endpoints. So here's a power series. Okay, so this is a known power series that we've seen before. Even if we haven't seen it, we can still test it. And so we're going to test this first of all with our ratio test. So we're going to set this up as the limit as n approaches infinity. So we have in our numerator, we have our an plus 1. So it's going to look like this, negative 1 to the power n plus 1. We have the x to the power of, I'm going to rewrite that. So we're going to have x to the power of 2n times 2 times n plus 1 plus 1. So that's going to be x to the power 2n plus 3. In the denominator, we're going to end up with 2 times n plus 1 plus 1. So that's going to give us 2n plus 3 in the denominator. For the other term, we're going to use negative 1 to the power n, and we end up with x to the power 2n plus 1 over 2n plus 1. So we're going to group some of these terms together. So I'm going to group these terms together. And so it's going to look like this, the limit as n approaches infinity, and we're going to end up with negative 1 to the power n plus 1 divided by negative 1 to the power n. That's just going to give us a factor of negative 1. For the other terms here, I'm going to group together the x powers. So we end up with 2 to the power, x to the power 2n plus 3. So I'm going to rewrite that as x to the power 2n plus 1 times x squared. So that's going to give me my 2n plus 3. And then in the denominator, I'm going to end up with x to the power 2n plus 1. Okay, so that's grouping those terms. And we can see that we're going to have some factors of 2, x to the power 2n plus 1 cancel out. We're going to be left with x to the power of 2. And then lastly, we're going to group together these terms here, the 2n plus 3 over the 2n plus 1. The 2n plus 1 ends up in the numerator. So 2n plus 1, and then the 2n plus 3 ends up in the denominator, and we're going to do the limit of that going to infinity. Okay, so we have some things canceling out here, so that red expression is going to simplify to 1 when we do the limit. So we have the limit as n approaches infinity. We have that negative 1 term. We're going to end up with x squared. In fact, I'm just going to write it like this. We have negative 1. We have x squared. And then we're at 2n plus 1 over n plus 3. That's going to end up being equal to 1. So when we apply the limit for that, I'm not going to apply the limit yet. I'll do that in the next step. So this is going to end up being equal to 1. Okay, so then the last step here, I'm going to actually apply the limit, and I know that this is going to be equal to negative absolute value of negative x squared, and I'm going to put the plus times 1 in here just to show that what happened to the red term. The red term became 1, and this must be less than 1. Our interval so far then is we have negative x squared is less than 1. Now we can interpret this as x squared is less than 1, which then we get x is less than 1, x is greater than negative 1. So there's our radius so far. Now to find out the interval, we need to test the endpoints. So we're going to first of all test x is equal to negative 1. And I'm going to put that into my original series. So I end up with negative 1 to the power n. The x now becomes negative 1, and I have 2n plus 1. And then the denominator is 2n plus 1. Okay, so I can group my negative 1 base, and I have negative 1 to the power of 3n plus 1. And the denominator is essentially a version of harmonic series. Now we just have to determine whether this alternates. And because of the 3n, the 3 there, it's gonna alternate between, if I plug in some values, n is 0, I get 1, n is 1, I get an even, n is 2, I get an odd, n is 3, I get even. So switching between even and odd, so this means that this is our harmonic series, and essentially it's alternating. Okay, so therefore it's convergent. So we will include that endpoint of negative 1. Then we move on to the other endpoint. We test x is equal to positive 1. When we do that, we're going to end up with the sum from n equals 0 to infinity. So it's the same expression, negative 1 to the power n. So I could just use 1 in green here. Instead of negative 1, I'm going to use 1 to the power of 2n plus 1. And that ends up giving us 2n plus 1 in the denominator, n to the power here, n to the power 1 to the power 2n plus 1 just is 1. So what we end up with is an alternating harmonic series again. So this is our alternating harmonic type. So although it's not quite a harmonic series, it's a harmonic type. We know it alternates, it goes to 0, therefore it's convergent. Okay, so then we can include that endpoint of 1, and so that our interval now looks like this. So our interval of convergence, we include the endpoint of negative 1, and we include the endpoint of positive 1. So this represents our interval of convergence. Now our center of convergence, we can work out from this expression here. For we can work out the center, I'll do this in yellow. Our center can be worked out from here because we know that we have x squared between 1 and negative 1. Well, that determines our center is at 0. There's no horizontal shift in that expression. The center is at 0. The radius the radius of convergence is equal to 1, because we know that we have from one side we have 1, the other side we have -1, so our radius is 1. Now we don't really need that negative in there. We should actually get rid of that negative, and that establishes our center and our radius. Our interval then works out to be -1 to 1.